So hello guys, in this video we will look at a couple of topic A4 questions on rigid body mechanics. I plan to make this into a series, so I will be making a couple videos. In each video we will look at 5 questions from this topic. All of these questions are from the Cambridge IB textbook. I think that this is one of the best textbooks if you want to look at the theory and do some practice questions. They provide quite a nice variety of questions we can practice with, and they are likely quite similar to exam style questions as well. When I was preparing for my exams and during the year, I really like to use this book. It really has good explanations and thorough questions that touch every part of the syllabus we need to know. So in the first question, we have a disk. It has an initial angular velocity, so it's rotating with an angular velocity of 3.5 radians per second. And after 5 seconds, we are told it has increased its angular velocity to 15 radians per second. So we can say this is omega 1, this is omega 2. And we're asked to find the angle through which the disk has turned. So to do this, we can simply use one of the equations that we have used. So from the old mechanics, from simple kinematics, we know that S is equal to V plus U times T over 2. In rigid body mechanics, we have a very similar question where we just have, instead of displacement, we have the angle, and instead of linear speeds, we have angular speeds. So omega 1 plus omega 2 times the time divided by 2. So all we need to do here is plug everything in, like this. And then, well, here we have time, so the time is 5 seconds. And then we divide it by 2, so that we find that this will be approximately 46 radians. Alright, and then in the next problem, we're given that a body is rotating about an axis with an angular velocity of 5 radians per second. So again, we have this, let's say, disk rotating at an angular speed of 5 radians per second. And we're told it also has an angular acceleration of 2.5 radians per second squared. We need to calculate the angular velocity after it has turned through 54 radians. And well, here again, in kinematics, we have the equation v squared is equal to u squared plus 2as. Here we have the identical one, only with rotational quantities. So we have the final angular speed is equal to the initial angular speed squared. We can say final. And so, well, the initial here and the final here, and then plus 2 times the angular acceleration times the displacement, which in this case is an angle. So we pretty much know everything. We know the initial speed is 5, and then we just add 2 times 2.5 times 54. So we get that this is going to be, well, we also have to take the square root of this. So we take the square root of this, and then we find that this will be about 17 radians per second. And then in question 3, we have a similar question. We're given the initial angular velocity, we're given the final angular velocity, and we're told in how many revolutions it has created this angular velocity, and we need to find the angular acceleration. So here as well, we need to use the same formula. So the final angular speed squared equal to the initial plus 2 times the angular acceleration times the displacement. So here we are told 20 full revolutions. This is also quite commonly done by IB. They expect you to know that 1 revolution is 2 pi degrees. So 20 revolutions will be 20 times 2 pi radians. 1 revolution is 2 pi. So now we know everything. We need to solve for A. So we know the final speed is 12.4. And then this is equal to 3.2 squared plus 2 times the unknown times 40 pi. And well, we can simply rearrange this equation and find that this will be 0.57 radians per second squared. All right, now we will move to a little bit more difficult problems. So we have a uniform plank. We're told that the plank itself has a weight of 450 newtons and it is 5 meters long. We have this 120 Newton block in the middle, 2 meters from the left pivot, and we need to calculate the force at each support. So what we can do here is, at the start when we're still learning these problems, we can always draw a free body diagram. So we just draw the beam and we just draw all the forces that are acting on it. So we have two supports here, A and B. Let's say that this is support A, this is support B. So in these types of supports, we need to learn that the only type of force that can arise is a vertical force. It does not prevent motion in the horizontal direction. If we would see something like this, a pivoted structure like this, and then we have a beam, this kind of support is one that only allows rotation in this axis. It does not allow the rod to move left and right or up and down. It only allows it to rotate around this pivot. Now here it seems like we just have this triangle and then we put the plank on top of it. So if we were to push the rod from the right, it would just slide. But since there are no forces acting in this horizontal direction here, we don't need a force to support that type of motion. So that means that A and B, we can only have vertical forces that prevent the rod from going up and down, in this case down. So whenever in free body diagrams we have to make some forces or replace these supports with a force, we always want to replace them with positive forces, FA and FB. We don't really need to think here, we can always just put them as positive. If they are negative, then our equations will tell us. So these are the two unknowns that we have to replace because we took away the supports. And then we have one force here acting downwards of 120 newtons, 2 meters away from the block. And we're told the plank also has a uniform weight, which means that we need to account for the weight of the rod itself. And in all of these IB problems, we just take the weight to act through the center of mass of the rod. So we just draw it straight into the middle, and it's going to be 450 newtons. And this here is going to be 2.5 meters. So now we have everything we need. We can write up the equilibrium reactions. We can write up equilibrium reactions in the translational sense, what we have already done. So we can say that the sum of the x component of the forces is equal to 0, and the sum of the y component of the forces is 0. So that means that the body is not moving up or down or left or right. Now here we have no x forces, so this equation isn't so useful for us. However, for the y forces, we can see that we have a positive Fa, we have a positive Fb, as they're pointing upwards, and then we have a negative 120 newtons and a negative 450 newtons. So from this, we can see that Fa plus Fb is equal to 570. So this, we have now one equation, and then we can make now a rotational equation. We can say that the net torque on any point has to be 0. So the net torque, so to say, has to be 0 because the body is not rotating. If there would be a torque, then the body would rotate in some way, but we are told that it's at equilibrium, it's obviously not going anywhere. So what we need to do is select a point anywhere on the structure. It doesn't even necessarily need to be on the structure. We just need to take a point and write the torque around that point. So usually if we think a little bit, then we can choose these points very smart, because what we know about torques is that, for example, if we take this point as the pivot, point A, then any force that passes through the pivot will not supply any torque. So for example, Fa, if we take the pivot at A, then the force at A is not going to create any torque around that point. It will not make point A rotate. Torque, the forces that have torque always have a distance from the pivot. So for example, if I would put a force over here, then it would have this arm, this is the distance, and that's how much it would rotate in this direction. It would be the force times that distance, that perpendicular distance. But here for this force, the distance is 0, it's on the axis of the pivot, so it has a torque of 0. And that's why, if let's say we write this torque on point A, then we don't even need to consider this force of A, we just need to consider the other three forces. Now what we need to make sure is that we select a clear direction to be positive and negative. Doesn't really matter, it's just important to stick with it. So usually the convention is that counterclockwise is positive and anti-clockwise, so counterclockwise is positive and anti-clockwise is negative. This is usually the convention. You can do it the other way if you like, it doesn't really matter, but I'll be doing it like this. So let's start with the force at B. We see it's going to have a torque. It will make the whole system rotate around point A this way. So that means it's going to have a positive torque. So the torque is equal to force times the arm of the force times the distance. And well, it's simply going to be this 5 meters. If we draw a perpendicular line from this axis to this line here in a perpendicular way, then it will be 5 meters. So we write 5 times FB. And then we have two other forces. So what that will mean is that, let's look at the 450 Newton one. This will be negative as it wants to rotate it this way, clockwise. So what we can say is that the arm of this force is now just going to be 2.5 meters, because this distance here is 2.5 meters. So we just say 2.5 times 450. And similarly, this 120 Newton force is also going to have a torque around point A. It's also going to be negative. So it will be minus 2 times 120. So if we rearrange this equation, we will find what FB is. So we just have this single equation for FB, and we will find that it is 270 newtons. And now if we remember back, we have already written this equation here. So all we have to do is plug in FB, and then we find that FA is equal to 570 minus FB. So 570 minus 270 will give us 300 newtons. And we have calculated the sizes of the two forces here. And we see that both forces came out as positive, which means that we have taken the forces in the correct direction in our free body diagram. If they would be in the opposite way, if we were going like minus 270 newtons, it would mean that point B is pointing in the opposite way as we took it on our diagram. So that's how you solve this. And we will have a similar question as the last question of this video. So here we have again a support. We again only have two supports like this, so we will only have vertical force components arising in the supports. And we're again told the plank has a mass of 30 kilograms. So it's going to have this 30 times 9.8 Newton force acting downwards through its center of mass. We need to calculate the largest distance x to which a boy of mass 40 kg can walk without tipping the rod over. So in these types of problems, when we have to calculate something that is just on the verge of happening, like just tipping over or just rotating, what we need to consider is the boundary condition. So like, when would it start tipping? At what distance of x would it be exactly that it's just about to start tipping, but it's not tipping yet? And well, the way we can define tipping is if the whole system turns around this pivot, which means that the force here, the force in this pivot, let's say again this is A and this is B, is 0. So there's no more force in this pivot, then that means that this rod has pretty much lifted off the surface. So we need to find at what distance of x that happens. And well, what we can do is simply write the torque equations around point B here. Because if we assume this tipping case, then what we say is that FA is equal to 0. And then simply, as in the previous question as well, simply with one torque equation, if we choose our point correctly, we will just eliminate one of the forces. But here FA is 0 anyway, so it doesn't really matter where we would write it. But let's say I want to write it at point B. So let's see what forces are acting here. We have this. There's a support force at B. However, by writing the torque around this writing the torque around this point, again, we don't care about what FB is. So by writing it there, we don't even calculate it because it's simply not important. So what we will see here is that we will have this force and the weight of the person. So that will also be acting down here. And we're told the person is 40 kilograms, so that will be 40 times 9.81 as the force. And so we pretty much see that there are only these two forces acting on this point. So let's see. This force would want to make the system rotate this way around the point. So that's clockwise, so we can say that's negative. So we say minus, so the torque has to be 0, and then this will be minus 40 times 9.81. It has to be 0 because at the moment it's 0 here. It's just not rotating. And then the other force is going to be rotating counterclockwise, so we take that as positive. And so that will be 30 times 9.8. And of course, we need to consider the distances as well. So here the distance is going to be x. So the arm of this force is going to be x. And to this we add 30 times 9.8 times 0.8. So now we just have this equation for x. We can rearrange this for x and we get 0.6 meters. So that is how you solve the last question. And in the following parts of this series, we will look at a couple more, perhaps more complicated questions from this topic.